Hello and welcome. If you're in medicine, you're constantly dealing with screening tests. But how confident are you really when it comes to interpreting those results? It's not always as simple as it looks. So today, we're going to build a powerful toolkit to get you from that feeling of confusion to real clinical confidence.
All right, let's just jump right in with a question. You hear about a new test, and it's 95% accurate. Sounds amazing, right? I mean, that's an A grade. It seems like a total no-brainer to start using it immediately. But the real answer, the one that makes medicine so interesting is, it depends. And by the end of our time here, you're going to know exactly what it depends on.
So, first things first. We have to lay down a solid foundation. Let's get crystal clear on the fundamental purpose of a screening test. What is it we're actually trying to do when we screen a whole bunch of people?
Now, you might just skim over a definition like this, but hang on. Look at that last part, among an apparently healthy population. That is everything. This is the absolute key. We are not testing people who are already sick to figure out what's wrong. No, we're testing people who feel totally fine, who seem perfectly healthy, all in the hopes of catching a disease early. That is a massive distinction.
Okay, so every single time we run a test, there are basically 4 ways it can all play out. The test can be right in 2 different ways, and you guessed it, it can be wrong in 2 different ways. If you can get your head around these 4 outcomes, you've basically mastered test evaluation.
And this little box? This is it. This is the Rosetta Stone of screening tests. It's called a 2x2 table, or sometimes a confusion matrix. It might look simple, but it unlocks everything. Let's walk through it with a made-up example. Imagine we screen 1,000 people for diabetes. Now, in this group, we happen to know that 150 of them truly have diabetes, and the other 850 don't. Let's see how our test did.
The best way to think about these 4 boxes is as the 4 main characters in our little clinical story. You've got your heroes, the true positives and the true negatives. They got it right. Then you've got the villains. The false positives, well, they cause a lot of unnecessary stress and extra tests. But the false negatives, they're the most dangerous, giving people this false sense of security while a disease continues to go undetected.
So, we have our 4 characters, our 4 outcomes. Now what? How do we use them to figure out how good a test actually is? Well, there are 2 really important numbers that are like a test's DNA. They're baked into the test itself, and they don't change no matter who you're testing.
And those 2 numbers are sensitivity and specificity. Think of it like this. Sensitivity is the test's ability to catch the bad guys. Its job is to find everyone who actually has the disease. Specificity, on the other hand, is like a good security guard. Its job is to correctly identify and let all the healthy people pass through without any fuss. These are fixed properties of the test.
Let's go back to our diabetes example. To get the sensitivity, we only look at the people who actually have the disease. That's 150 people. The test correctly identified 120 of them. So we take our 120 true positives, divide by the 150 total sick people, and boom, we get 80%. So this test caught 8 out of every 10 people with diabetes, which sounds pretty good, but it also means it missed 2 out of every 10.
Now let's look at the other side of the coin, specificity. For this one, we only look at the healthy people. There were 850 of them. Our test correctly cleared 770 of them. So, we divide 770 by the 850 total healthy folks, and that gives us a specificity of 90.6%. Again, pretty good. It correctly cleared about 9 out of 10 healthy people. But it also rang a false alarm for about 1 in every 10.
Okay, take a deep breath, because this next part, this is probably the most important concept in this entire explainer. We've talked about sensitivity and specificity, which is how a test performs in a perfect world, like a lab. But what happens when we take that test out into the real world, where the number of sick people in a population, what we call prevalence, changes absolutely everything?
This brings us to something called the positive predictive value, or PPV. And folks, this is the number that really matters to the patient sitting right in front of you. They don't care about sensitivity or specificity. They have one question and one question only. Doc, my test came back positive. What are the chances I actually have this disease?
So, in our example, the PPV is only 60%. How is that possible? Well, let's look at everyone who tested positive. That's 120 people who were true positives, but also 80 people who were false positives. That's 200 positive tests in total. The PPV is just the 120 true ones divided by that total of 200, and that gives you 60%. Just think about that for a second.
Even with this pretty good test, a positive result still means there's a 40% chance it's just a false alarm.
So if you only remember one thing today, please let it be this. The predictive value of a test is not a fixed number. It is completely, totally, dramatically influenced by how common the disease is in the group you're testing. If you use the same test in a high-risk population, the PPV shoots up. But use that exact same test in a low-risk population, and the PPV can plummet.
And hey, this isn't just theory. Check out this real-world data from India. We're looking at the exact same HbA1c test for diabetes. In urban areas, where diabetes is more common, it has a strong PBV of 82%. But take that same test to rural areas, where diabetes is less common, and the PBV craters to just 45%. A positive test there is actually more likely to be wrong than right. This is why we don't just screen everybody for everything.
Now on the flip side, we have the negative predictive value, or NPV. This is often the good news part of the story. In our example, 800 people tested negative. 770 of those were true negatives. So we divide 770 by 800 and we get an NPV of over 96%. This means a negative result gives you some powerful reassurance. If your test comes back negative, you can be very, very confident you don't actually have the disease.
Okay, so we've got the concepts down. Now let's see how all this moves from being just numbers on a page to making huge public health decisions that affect millions and millions of lives. This isn't just an academic exercise. This is the bedrock of public health policy.
What's so cool here is you can see how the strategy completely changes depending on the disease. For something like TB, you cannot afford to misdiagnose someone as positive, so you need a test with an incredibly high PPV, like the Gene Expert. But for malaria in certain remote areas, the main goal is often to quickly and confidently rule it out. So there, a test is chosen for its amazing 99% NPV. See, it's all about picking the right tool for the right job.
And these huge nationwide decisions aren't just made on a whim. They're guided by this classic framework developed way back in 1968. The Wilson and Youngner criteria make sure that a screening program isn't just accurate, but that it's also ethical, practical, and ultimately that it actually helps people. The bottom line is, it has to do more good than harm.
So, I'll leave you with a final thought to chew on. Imagine a disease that's incredibly deadly, but also very rare. And the treatment for it, it's really risky. Now, what's the worst mistake to make? Do you choose a test with super high sensitivity to catch every single possible case, even though it means you'll end up giving a risky treatment to some healthy people? Or do you go for high specificity to protect the healthy, even if it means you might miss one of those rare fatal cases? There is no easy answer. And learning to navigate that kind of uncertainty, well, that's the art and the science of medicine.